So good morning, everyone. I'm going to show you a presentation on my project, which is about homomorphic encryption and cloud computing. So first, I will start with the objectives of the project. So, yep. The first thing is to provide a general purpose C++ API for homomorphic encryption and cloud computing. This is actually regularly asked by the cryptographic community online. The second objective is to push currently available technologies to their limits. Third objective is to implement a simple but useful data analysis operation, which is the average operation. And the last thing is to prove homomorphic encryption can be used today for some operations, not all of them, but some operations. So now I'm going to show you how cloud storage and cloud computing works today, so you grasp what homomorphic encryption could solve. So, yeah, it's pretty slow. So, in this example, the first one is about cloud storage. So, in the cloud storage case, the client just encrypts his data, is going to transmit it to the cloud storage, which can store it in encrypted form, and when the client needs it back, he will just download it. Yep.
So actually, because we're in a small room and
yep.
This microphone doesn't work well, so
okay.
Sorry, we need it for recording. You can just turn it down, maybe.
Okay.
But no, you can just maybe.
Oh yeah, sure. All right, fine. All right. Let me. I would just word it like this, yeah? Okay. All right, so in this case, you can just store the data in encrypted form. The client will just download it when needed and decrypt it. So the cloud computer, the cloud storage computer doesn't know what the data is. But on the cloud computing version, it's slightly different. Now the client does the same thing, but the cloud computer will have to decrypt the data to do some processing on it. And this means there are two risks associated with this. The first one is a privacy risk, because the cloud computer can actually know what your data is and what your result is from the operation you requested. And the second risk is, this is the hacker kind of, I think you understood that. And because the cloud computer is a high-value target for a hacker, if he gains access to it, he will be able to see your data and your result in the cloud computer. So now I will show you what homomorphic encryption can solve, especially these two issues, privacy and security issues. So this is the same diagram as before. Now I will show you how homomorphic encryption modifies this diagram conceptually. It basically replaces all this by this, which means processing is going to be executed on ciphertext, on encrypted data, instead of plain text. So this means the cloud computer doesn't know what it is doing, and a hacker cannot gain access to your data if he hacks into the cloud computer. Right. So this is a concrete example. Conceptual is not really what is happening, but so you have 17, you encrypt it. The cloud computer will, for example, add 3 and multiply by 5, and when you decrypt it, the result will match the operation done on the plain text. So, but the issue with homomorphic encryption is time and resources. The encryption and the homomorphic operation are really time expensive. They take probably 1 million or 10 million times more time than normal processing on plain text. So that's the issue I'm going to tackle. Now I'm going to talk about the technology today. I will start with a bit of history. So homomorphic encryption has actually been around for many years. For example, in the RSA scheme, you can do multiplications between ciphertext, but before 2009, it was impossible to do both addition and multiplications, and this means you're quite limited. So you can only multiply to ciphertext, which is kind of useless. But since 2009, fully homomorphic encryption, also called FHE, allows to do addition and multiplications on the ciphertext. Now, in 2009, someone called Craig Gentry, a student in Stanford, found it was possible to do it. And in 2011, it was practically possible on a computer to do it, thanks to Craig Gentry and Shay Halaby. Since then, yeah, there have been many fully homomorphic encryption schemes designed and many software libraries, such as HLib, which is one of the main ones maintained by Shay Halaby from IBM. All right, now I'm going to talk about ciphertext noise because it's crucial to understand that. So each ciphertext in the homomorphic world has a noise associated with them, which is added from randomness, which is added for security purposes. Now the thing is, with homomorphic operations, such as the multiplication, the noise will grow. And when the noise reaches a certain threshold, the ciphertext won't be able to be decrypted anymore. So you have to maintain that noise lower to this threshold, otherwise you won't be able to see what the result is, which is pointless. So now I want to highlight with the multiplication and addition operations that multiplication had a lot more noise than addition. I will demonstrate that in the next slides as well.
So just a
Yep.
quick question. So normally when we save our file in the cloud, where the noise come from? Where does the noise come from? You mentioned noise, right?
Oh, you mean, well, it just added, for security purposes, its randomness to the ciphertext. And this is because you have an initial noise, and then the noise will grow if you, for example, multiply two ciphertext, then the result will have, like, not twice, but a lot more noise, for example.
Yeah.
Okay.
So essentially you are saying that the noise was added when we do the encryption.
Yep.
Okay, good. Yeah.
So now to counter this growing noise, we have two techniques. We have the bootstrapping and the level homomorphic encryption. The bootstrapping was the first technique invented by Craig Gentry in 2009. It allows a fully homomorphic encryption, which is great, but it is very slow and expensive in terms of resources. On the other hand, the other one used in the BGV scheme in 2011 is not a fully homomorphic encryption scheme. It is almost. It allows you to do a certain number of operations, which depends on the parameter, level parameter called L. And this is way more performant, but for low values of L. And while you're still bounded to a certain number of operations. And the smaller L is, the faster the homomorphic operation will be. So this means, for example, if you have a simple operation and you require a very low value of L, then you can simply do this really quickly. So that's great. It's way better than the bootstrapping thing. I will explain that again later. So now I'm going to talk about the library I used, which is called HLib. So yeah, it is the second most performant library I found. It is portable, flexible, tweakable, and it is well documented and maintained on GitHub as well. And it supports many technologies, bootstrapping, level homomorphic encryption. It provides two basic operations, the addition and multiplication. And one important thing is that you can use the SIM mode, which means single input, multiple data. So for example, this will show you how this works. You have two vectors of numbers. You encrypt them, and you multiply the two ciphertext. The decrypted result will match the component-wise multiplication of each number. And this means you save a lot of time, noise, everything. It's a big step forward because this will only add once, increase once the noise, and you don't have to process each number separately. All right, so now the missing part, I will explain where my project fits. So yeah, there are many schemes, many libraries. There are already a few built applications, such as the remote end-to-end voting, but there's no general purpose API for number operations, such as comparison or division. So now the implementation of the project. I will start with where I started, which is using what HLib provides to do logic gates. So after a lot of thought, the only way to design your operation was to use binary. So you do calculation in the field F2. And this means, as you can see, the addition in F2 matches a XOR gate, while the multiplication matches a NAND gate. So these are the two first gates I've been designing, this was quite straightforward. Then I had a big issue with the NOT gate, because if you want to do anything like an OR gate or something, you will need to have a NOT gate. So the NOT gate is the addition with a constant 1, right, which seems easy. But the thing is, the computer shouldn't know what a 1 is, otherwise there's no point to use the homomorphic encryption. So, yeah, how does the cloud computer know what a 1 is without knowing it? So this is the method I used for this. I will tell you why the cloud computer doesn't know what a 1 is. So the client generates his key pair, creates a vector filled with 1s as for the same thing, and encrypts it, sends a ciphertext, and then the computer assigns it to a global 1 ciphertext, which will be used for all the NOT gates. And why the computer doesn't know is because the encryption of the vector 1, 1, 1, 1, 1 is completely different from the encryption of the vector, for example, 1, 1, 1, 0, 1, 1. And this is thanks to SIMD, because all right, a vector is usually can usually be like 1024 slots in the vector. So this is quite huge, and the only thing the computer learns is an eventual SIMD result filled with only 1s, which is unlikely to happen due to the high number of slots, as let's just say. So from then, I've been so yeah, to represent an n-bit number, this is how it was done. So an n-bit number is actually n ciphertext. So, well, small n ciphertext. Each ciphertext represents a bit of the number, and you will have a big N numbers where the big N is the number of available slots in the vector. So now, this is a quick example so you understand how this works. So, for example, this Euclidean division circuit takes into input 2 binary numbers, so of n bits each. And these are actually n ciphertext each, and it outputs n ciphertext and n ciphertext, which are 2 binary numbers. So, yeah, that's a big diagram of everything that I've done. So, first, the yellow things are the logic gates. Then I've been implementing combinational circuits, mostly the basic ones, and from then, I've been implementing sequential circuits, which don't require a clock, actually. Just in the code, it's just a for loop using the homomorphic combinational circuits. And from these sequential circuits, I implemented some more complex circuits, such as the multiplication circuit or the Euclidean division circuit. So I won't go through all of them. I will just quickly show you some characteristics. All right, now I'm going to talk about results and evaluations of the circuits, homomorphic encryption, and so on. So I'll start with logic gates again. There are 2 kinds of logic gates. There are the ones only using an addition, a homomorphic addition operation, and the ones using a multiplication operation. As you can see, the one using a multiplication operation requires a lot more time because of the noise, again, because the noise grows very quickly, so you have to compensate with a higher level parameter, so it will require more time. And on the other hand, gates using only the addition, such as the NOT gates, well, they require barely no time to execute. So this is a quick plot of the M2A ratio. The M2A ratio is the time needed for the multiplication operation to complete, divided by the time needed for the homomorphic addition to complete. And yeah, and as you can see, the multiplication had between 12 and 34 times more noise than the homomorphic addition. So from now on, we'll call it complexity, because all the complexity is related to this homomorphic multiplication, mostly. So now a bit of level and time, complexity, sorry. So this is the number of multiplication required for all the circuits. As you can see, it matches, again, the time in milliseconds for each circuit to complete. So for example, this is relatively fast. This is 1 second, but it is for 1024 operations, so it means it would be 1 millisecond per operation. These are still some combinational secrets, so they are not that useful. Now, sequential secrets, which could actually be useful. These are flexible with the number of bits of a number. As you can see, the complexity is linear against the number of bits of the input numbers. So this is good, because later on you will see some are exponential, so this will be worst. And as you can see, this is another graph showing, all right, the yellow line is the time per operation for 1,800 slots. The gray one is the overall time, and this is the same thing for 1,024 slots. And what you can see is that if you increase the number of slots, the time per operation will be way lower, even if the overall time will take a longer time. So this is great if you focus on the overall throughput of the system and not on the overall time needed. All right. And finally, the arithmetic circuit, which concerns binary multiplication, well, more complex circuits. Now the complexity is exponential, so this is quite bad. It means, for example, over 8 bits, usually, for example, the multiplication, you cannot do anything. It doesn't work. So, yeah, exactly. Arithmetic circuit become really unusable as the number of bits n grows. All right, so this is the minimum level required. So all the secrets, amongst them there's the, for example, the average secret, which is the most complex one. And yeah, you couldn't go above 3 bits, otherwise it doesn't work. So it requires too much time, it requires like hours. So yeah, it doesn't work. And you can see the minimum level is very high for the average secret. This is due that it uses the Euclidean division secret, which requires high level as well, as you can see. On the other hand, the multiplication secret and the some of the fast average secret, which only uses shifts, is way faster. And now this is a time plot. So this is the number of bits for each secret. So as you can see, the multiplication one can actually be used, so that's great. If the number is less than 8 bits, or equal to 8 bits. For 9 bits, the time raises really hugely and it becomes unusable. So yeah, it's not timely useful anymore. It's really ridiculous to have 1 second for each operation. So now conclusion. There's a lot of things in this. So yeah, we just showed that some operations are actually not that costly in terms of time. They can now be used like the binary additions, subtractions, comparisons. You can do binary fast averages using shifts and additions. And you can do binary multiplications for numbers up to 8 bits. You can also use, develop some multiplexers as well. So you can still do some simple circuits. The code is also robust. 75% of the API code is covered by unit tests and is open source, well documented, I hope, and it's easy to set up and use and compatible on all platforms. There's a lot of future work possible. All right, first you can change the algorithm used in the sequential and arithmetic circuits. For example, the Euclidean division uses a quite complex algorithm, but I'm sure there's something more performant. And you can add more homomorphic secrets, such as a parity check secret, for example. Also, for very complex secrets requiring a lot of time, you could use bootstrapping instead of the level homomorphic encryption, because bootstrapping is actually faster when the level parameter is really high, so when you have a really complex secrets. And you could also use actually use multiple cores of the CPU. For now, it was only using 1 core of my CPU, and there's also a library quite interesting called QHE, which is based on CUDA and uses NVIDIA graphic cards to perform homomorphic operations. and it's 50 to 100 times faster, so that's quite nice. But it's not portable, that's the thing. You really need a NVIDIA graphic card and thing. But for cloud computer, that would be quite useful. Yep. And I'm quite happy as well because it's actually used by computer science masters in Canada. But, so yeah, actually it's useful, so that's great. And yeah, that's all. Thank you for listening.